So when we last left off, we discussed formula methods for determining the charge of each ion in an ionic compound. There's an alternative method to figure out the charge of your cation in a neutral ionic compound. And in this method, first you figure out the charge of the anion using periodic trends and the common charges for the polyatomic ions. And then what you do is you take the subscript of each ion and you place it in the charge for the opposite ion. So what do I mean by that? So let's say you have, for example, iron chloride. We know that we can reverse cross our charges, and that in turn gives us iron 2 plus and Cl minus.
So essentially, it's like cross multiplication of the denominator, or not denominators, but the, you know what I mean, the subscript.
Yes. So let's do a guided example for this process. So first and foremost, it's asking what is the charge of cobalt in cobalt sulfate. So first things first, we write out our formulas. And then all we have to do is we reverse cross our charges, and that gives us cobalt 3 plus and sulfate 2 minus. And that matches our predicted charge for sulfate. Next, we're asked what is the charge of the anion X in scandium X3? So first and foremost, we write out our formula, and then we reverse cross our subscripts. I just put a 1. The 1's implied, but it makes it easier to see the charges, so it's worth putting the charge. Remember, your anions are negative, your cations are positive.
Oh, will we get penalized if we have like miscellaneous numbers? So if we like leave the 1 there, will we still get penalized or no?
In the final formula, yes. Yes. If I ask for the formula, it should not have extraneous numbers attached to it.
Okay, thank you.
So let's try to apply this method of determining the charge of your cation to the following problem. So let's take about 3 minutes to work on the following 2 examples, and then we'll come together as a group to discuss. And don't be shy to message your proposed responses via the chat feature or unmute and ask questions via Zoom.
Okay, are these posted already, or are we just working on the notes?
You're just working on the notes. They'll be posted today or tomorrow.
In the future, are the quizzes just going to be posted after, or are you going to post it up?
They'll be posted concurrently. These ones are just these specific nomenclature questions. I'm just trying out a few methods to set them up where they're most reflective of and most open-ended. So I was trying out a few different methods, but Canvas was being a little bit problematic when I tried to set up some of the more open-ended grading schemes for nomenclature. So you'll see these questions pop up today or tomorrow once I've decided on a version that you'll see similar to that on the exams. So that way you get used to answering these questions in Canvas, similar to that which you'd enter in for an exam. And I already see a few responses in the chat. Let's take a few more minutes and we'll discuss in about a minute and a half. Let's try to get a few more responses in the chat and we'll discuss in about 30 seconds. Okay, so let's discuss this next example. So we have nickel acetate. So we're going to reverse cross our charges, and that in turn gives us nickel 3 plus and acetate with a -1 charge, which matches our expectations. Next, we're asked, what is the charge of the anion X in silver X? So we're going to write out our full formula, and then we're going to reverse cross our subscripts to give us the charge. So we have silver plus and X2 minus. Do these examples make sense? Any questions on these examples?
So for the first one, it's just the 3 that's outside of the parentheses. That would be the answer.
Yeah.
And I3 plus.
Yeah, exactly.
Okay.
Any other questions I can address? If not, let's keep going now. So there's one important side rule that you need to remember. If the charge of a single ion does not match the known charge for that ion, you need to multiply your charges by a common whole number. So let's explain a little bit what I mean in the following example. So if we have nickel dichromate, Cr2O7 is known as dichromate. If we reverse cross our charges, we would get nickel plus and dichromate minus. However, if you look up dichromate, and if you recall the charge of the polyatomic ion dichromate, what is the charge? What is the charge of dichromate? 2 minus, exactly. So then, the question then becomes, as we can clearly see, these charges don't match. So then, what should we multiply our charge by to give us a charge of 2 for dichromate? What should we multiply our charge of dichromate by? What should we multiply our charge by? 2. Yep. Now the key thing, because ionic compounds are charge balanced, you're going to multiply both of your charges by 2. That in turn gives us nickel 2 plus and dichromate with a 2 minus charge. And everything is right with the world. Dichromate has the correct charge matching its known charge in our table of polyatomic ions. So let's do another example of this idea. So we have aluminum X. So we're gonna reverse cross our subscripts, and that gives us aluminum plus X minus. Now we know that aluminum is a 3A element, adopts a charge of +3. So then what we're going to need to do is we're going to need to multiply all of our charges by 3. That gives us aluminum plus 3 and X minus 3. Does this make sense to everyone so far? You just want to make sure that your charges match the known charge for your anions. Okay, so let's.
Why do you multiply the nickel by 2?
Because your ionic compounds are charge balanced, in order to, if you multiply the charge of dichromate by 2, you have to multiply the charge of nickel by 2 in order for the charges to still be equal.
Oh, okay.
Does that make sense?
Yeah.
Perfect. Any other questions I can address? Okay, so with that established, let's take a moment and let's work on the following 2 examples. Let's take about 3 minutes to assign the charge for the atoms in the following 2 compounds, and then we'll discuss in about 3 minutes. I see some reasonable responses so far. Let's get a few more responses and then we'll discuss. Don't be shy to ask questions via the chat or unmuting and asking your question verbally. And we'll spend about another minute and a half on this problem. I'm seeing some reasonable responses in the chat so far. Let's try to get a few more and then we'll discuss in about 30 seconds. It may not necessarily have to be simplified. You only simplify the ratio of subscripts. The charges don't necessarily have to be simplified. Okay, so let's discuss these 2 examples. So first and foremost, write out our formula. So we have copper 1, phosphate 1. We reverse cross our charges. That gives us copper plus and phosphate minus. However, we know that phosphate, what is the charge of phosphate? What is the charge of phosphate? 3 minus, yep. So we need to multiply each of our charges by 3. That gives us copper plus 3 and phosphate 3 minus. Let's do another example. Let's discuss this next case where we have Ca2y. Okay, we reverse cross our charges. That gives us calcium plus and Y2 minus. We know that calcium is a 2A element adopts a 2+ charge. So then we're going to have to multiply both of the charges by 2. That gives us calcium 2+, Y4-, and everything matches as it should. Any questions so far? Any questions so far? If not, let's continue on and tackle the next topic. So, in some cases, we can end up with metal complexes that are charged in nature. So in order to handle these charged metal complexes, we're going to have to go back to our original equation that states the total charge for an ionic compound is the sum of the total charge of each ion. So first and foremost, we determine the charge of the anion using periodic trends and common charges for polyatomic ions. And then what we can do is we can solve for the charge of our cation. So the only thing that's changed when we solve this modified equation for the charge of our cation is that now we have this total charge term, where this total charge is the charge of our metal complex. So let's show how we can use this equation to solve for the charge of our cation in charged metal complexes. So in this case, we have a complex with a -1 charge. So solving for the charge of our cation, which in this case is the charge of iron, we'll take our total charge, which is -1, minus the charge of our anion, which if we think about our anion for a moment, what is our anion in this case? What is our anion in this case? What is our anion? What's its identity and its charge? Hydroxide, yep, OH. And what is the charge of hydroxide? What is the charge of hydroxide? -1. So we have minus -1, and we have 4 hydroxide ions. So we put a 4 here, and then we divide by the number of our cation, which is 1. That in turn gives us a charge for iron of +3. So this would be iron 3+. Any questions on this example? Any questions on this example? The only thing that's new is for charged metal complexes, you have to account for the charge, the total charge of your complex. Any questions on this? Okay, so let's continue on then. So I'd like you now to take about 2 minutes to work on the following example where you're asked to calculate the charge of copper in the following copper chloride complex. And we'll discuss in about 2 minutes. Don't be shy to message me with your proposed charge assignment. And any questions you may have on this example. Yep, this one will be posted on Canvas sometime tomorrow for you to reattempt. And let's try to get a few more responses in the chat, but we'll discuss in about 1 minute. Let's try to get a few more responses or a few more questions in the chat, and then we'll discuss in about 30 seconds. Okay, so let's discuss this next example. So in this case, we're solving for the charge of copper. Our total charge in this case is -2. We're then going to subtract, and looking at chlorine, chlorine prefers to form the ion chloride with a -1 charge. So let's fill in our -1 charge. We have 4 chloride ions. Then we divide by our number of copper atoms, and that gives us a charge of +2. So we have copper 2+. Does this make sense to everyone? Any questions on this example?
So the -1, that's for chloride,
Yes.
and we're getting that from the table. I'm trying to find chloride. Like, how do we know it's a negative?
So this is based on periodic trends. So when we discussed periodic trends, non-metals that are in the main group adopt a charge equal to their group number -8. Chlorine in the periodic table is a group 7A element, so 7 minus 8 gives us -1. Does that make sense?
Yeah, I got it. Thank you.
Perfect. Any other questions on this example? If not, let's continue on and let's tackle the following set of problems. It's a fill-in-the-blank set of problems. So let's take about 5 minutes or 5 to 6 minutes, and let's fill in the blank each of the following 2 fill-in-the-blank problems with 3 reasonable atomic ions, 1 polyatomic ion, and for the top question, 1 transition metal, given the formula that I provided. So let's take about 6 minutes to work through this problem, and you're more than welcome to message me with your proposed responses, any questions you have about this example, and we'll discuss momentarily. Let's try to get a few responses in the chat, or at least a few questions in the chat, and we'll discuss in about 5 to 6 minutes. Any questions so far? Any proposed responses so far? We'll discuss in about 3 to 4 minutes. So your goal is to simply find at least 3 reasonable atomic ions, 1 transition metal ion, and 1 polyatomic ion that can fit in the blank for the first and second examples. As a hint, I would recommend trying to figure out the charge of this ion in the blank space. So in this case, the total charge is 0, so you can just reverse cross your subscripts to the charge. Otherwise, you can use the equation where your charge of your cation is equal to -1 times the charge of your anion times the number of our anion over the number of our cation. Both methods are valid. We'll discuss this example in about 2 to 3 minutes. I'm seeing some reasonable responses start to pop up in the chat. Let's try to get a few more responses so I can see how everyone's working through these examples and any common comments I can make about these questions. Any questions on this example? We'll discuss in about 1 minute. We're getting some reasonable responses so far, and let's try to get a few more responses in the chat so we can discuss. So let's discuss this first example just to provide everyone a little bit of guidance, and then we can tackle we can give everyone some more time and tackle the second example. Okay, so if we know the formula, then we can write our subscripts and we can cross our subscripts into the charge to get the charge of each ion. So this blank has a charge of +1. And chromate has a charge of 2-. This matches the tabulated charge of chromate. So now for blank plus, what group has a charge of +1? That would correspond to a group 1A metal. So that could be lithium plus, sodium plus, potassium plus. Hydrogen would not work because hydrogen is a non-metal. It forms an entirely different type of compound called an acid. For our transition metal, you can of course list any transition metal, such as, for example, copper plus, or you can list a fixed charge transition metal, such as silver plus. For our polyatomic ion, what polyatomic ion has a +1 charge? What polyatomic ion has a +1 charge? Ammonium, exactly right. So this is NH4 plus. Does this example make sense to everyone so far?
So we're only looking for a +1 charge for all of them?
Yes.
And why is that?
Because when we reverse crossed our subscripts, it indicated that in order to have this formula, the cation in blank must have a charge of +1. And we got that by taking the subscripts and crossing them up to get the charge. Does that make sense?
So then it could literally be any of those under group 1?
Yes, exactly. It's a pretty open-ended question in that sense. Any other questions on this example? If not, I'd like us to take what we've learned from that previous example and to try to answer the second problem. So let's give everyone another about 3 minutes and let's work on this next example. And we'll discuss in about 3 to 4 minutes. And don't be shy to message me your proposed responses or any questions in the chat function. And I'm seeing some reasonable responses in the chat. Let's try to get a few more and we'll discuss in about 2 minutes. And we'll discuss in about 1 minute. Okay, so let's discuss this next example. So first and foremost, we write out the subscripts and we cross our charges. So that gives us cadmium plus and blank plus. Now, if we think about the charge of cadmium, if we recall, the charge of cadmium is what? So what is the charge of cadmium? Two plus, exactly. Whoops, sorry. It should be blank minus. Let me correct that. So since cadmium has a charge of 2 plus, we're going to multiply each of our charges by 2. That in turn gives us cadmium 2 plus and blank 2 minus. So then, what elements or what ions have a charge of 2 minus? Is there a group of elements that adopt a 2 minus charge? What group are we thinking of here? Is there a group of elements with a 2 minus charge? (6A), yep. So your 6A elements such as sulfur, oxygen, selenium. Okay, and in terms of our polyatomic ion, there are a ton of them with a 2 minus charge, some of which would be carbonate. Let's try to get a little bit of variation. So sulfate, chromate, there are a whole number of polyatomic ions with a 2 minus charge. Okay, so that's that problem in a nutshell. Any questions on this example? If not, let's continue our discussion. So nomenclature often heavily relies on classifying compounds. So binary compounds have exactly 2 different elements. So for example, sodium chloride. We have exactly 2 and only 2 different elements. Now, these binary compounds can be ionic or covalent. Binary ionic compounds, we have 2 different elements. Whoops, one moment. And we have a metal cation and a non-metal anion. So binary ionic compounds contain a metal cation and a non-metal anion and exactly 2 different elements, no more, no less. Binary covalent compounds contain exactly 2 different elements covalently bonded, and binary covalent compounds are composed of 2 different non-metal elements. So examples of this would be carbon monoxide. Now, we don't just have to have 2 atoms. Another example of a binary covalent compound would be carbon dioxide, where we still have 2 different elements, but we have multiple atoms. Does this make sense to everyone so far? Let me just put a little shading on the oxygen atoms to indicate that they are, in fact, different elements. So, the reason why this is important is because different classes of compounds have different rules for naming those compounds. So let's talk about the naming rules. So for binary ionic compounds, class A in this distinction, we have a main group metal. So a main group metal and a non-metal. So first and foremost, when you're naming these binary ionic compounds, your first step is just to write the name of the metal cation straight from the periodic table. So this is why you're going to need to be familiar with your element names. Next, you're going to write the name of your non-metal anion, and you're going to replace the ending with IDE. Now, you're going to need to memorize the common stems in element names, which are shown here. Now, there are a few unique stems that often catch students off guard. So for oxygen, oxygen turns to oxide with the stem being ox. Phosphorus turns to phosphide with the stem being the phosp prefix. Nitrogen turns to nitride with the NITR prefix being the stem. Sulfur turns to sulfide. So these are some common stems that catch students off guard. So just make sure to be familiar with the common stems so you can name your atomic ions and atomic anions specifically. So to show an example of this, let's name a few compounds. So Na2O, so Na is sodium, so I'm going to write the name of sodium. And then for oxygen, as it's an anion, I write my prefix, my stem of ox, and then I change the ending to IDE. So this is sodium oxide. Note that ionic compounds, you don't have to specify the number of each cation or anion. It is implied by the charge. Let's do another example. CaI2 would be calcium. And then iodine turns to iodide. So the second problem, we'd get calcium iodide. Any questions on this process for naming binary ionic compound? Okay, let's keep going now. So let's do another guided example. So let's name the following compounds, and as a bonus, we're asked to specify the charge of each ion. So first I'm going to name this. So first we name our metal, which is barium. Next, we name the stem of our anion, which is the sulf stem, and we add the ending IDE. So this is barium sulfide. If we wanted to figure out the charge of each ion, we reverse cross our charges. We remember that sulfur typically adopts a 2- charge. So we multiply both of our charges by 2 to give us barium 2+ and S2-. This is just a separate part of the problem that I'm asking you to do. To name the compound, you just name your metal and then name your non-metal. ALN would be, we name our metal, which is aluminum. And then instead of nitrogen, we put the nit prefix, and then we end with IDE. So to answer the question, what is the charge of each of our ions? We write the subscripts. We reverse cross our subscripts. That gives us aluminum plus and nitrogen -1. We know nitrogen typically adopts a 3- charge following periodic trends. So we multiply both of our charges by 3. So this is the complete solution to both parts of this problem. And you will have to name a few compounds on quizzes and exams for sure. Being familiar with the names is really critical to tackling problems in which you're given a chemical equation or other information in word form. So let's now focus and let's work on the following example where we're asked to name the following set of 4 compounds and specify the charge of each ion. So let's take about 4 to 5 minutes to work on that example, and then we'll come together as a group to discuss. The charge of an anion is negative, while the charge of a cation is positive. So the metal cation will be positive, and the non-metal anion will be negative. So let's spend about 4 to 5 minutes working on these 4, and you're more than welcome to message me with your proposed solutions. I'm seeing some reasonable responses in the chat. Let's try to get a few more before we discuss in about 4 minutes. And the last compound on this list is still an ionic compound. And the first compound that's on this list, the symbol K, represents potassium in the periodic table. Let's try to get a few more responses in the chat, and we'll discuss in about 3 minutes. And if there are any questions, don't be shy to type them in the chat. Let's try to get a few more responses and we'll discuss in about 2 minutes. Okay, so let's discuss these examples. So first and foremost, for K2S, we're going to name our cation, which is potassium. For sulfur, we replace the ending with IDE. So sulfur turns to sulfide. So this is potassium sulfide. If we wanted to figure out the charges, we just take the subscripts and cross them into the charges. That gives us potassium plus and S2 minus. CaCl2, we name our cation, which is calcium. And then we name our anion, which is chloride. If we wanted to figure out the charge, we put each of our subscripts and then we cross the subscript into the charge. That gives us calcium 2 plus and Cl minus. Continuing on, for Ba3P2, we name our cation, which is barium. And then we name our anion, which is phosphorus, and we change the ending to IDE. So phosphorus turns into phosphide. If we wanted to figure out the charge of each of our anions, we reverse cross our charges. That gives us barium 2 minus, barium 2 plus and phosphorus 3 minus. Remember, the metal cation is always positive. The non-metal anion is always negative. Finally, for this last compound, we name our metal, which is boron. And then we name our non-metal, which is oxygen. We retain the stem and replace the ending with IDE. This is boron oxide. If we wanted to figure out the charge of each of our ions, we'd write the subscript and then cross our subscripts to give us boron 3 plus and oxygen 2 minus.
How do we know which one's an anion and a cation again?
The
Like,
metal,
for example, the last one, Ba3.
the metal is the cation, the non-metal is the anion. In general as well, the most electronegative element will prefer to be the anion, the least electronegative will prefer to be the cation. Does that make sense?
So, sorry, you're cutting off a little bit. Metal is a cation?
Yes.
Okay. Okay, thank you.
So the metal is the cation, the non-metal is the anion, and in general, the least electronegative element will prefer to be the cation, while the most electronegative element will prefer to be the anion. Does that make sense?
Yeah.
Perfect. So, if we wanted to write the formula of binary ionic compounds from the name, there are a few methods. So first things first, you're going to identify your metal cation from the name and using the periodic table. Then you're going to identify your non-metal anion by looking for the name that ends with IDE. Yeah, for binary ionic compounds, you don't have to specify the number of each cation and anion. It is implied by the charge. So for example, if you see the name lithium nitride, for example, the IDE ending tells us that our anion is derived from nitrogen. So we have nitrogen 3 minus. And from lithium, we know that we have lithium plus. Where do we get lithium plus from? Lithium is a 1A element. So then lithium prefers a +1 charge. Nitrogen is a 5A element, and so nitrogen prefers a 3 minus charge. Now that we have each of our ions with their designated charges, we write them out. and then we place the charge for each ion in the subscript of the opposite ion. And that in turn gives us Li3N for the formula of lithium nitride. As a last minute check, you can verify that the total charge of all of your cations and anions matches the total charge of your ionic compound. So 0 is equal to the charge of our cation, which is +1, times the number of our cation, which is 3, plus the charge of our anion, which is -3, times the number of our anion, which is, oh, let me just write it as 1 to avoid ambiguity. And that in turn, when we add our charges together, gives us a total charge of 0. So everything checks out as expected. Does this make sense so far? Any questions so far on writing the formula of an ionic compound based on the name? If not, let's continue on and let's try to write the formula for the following compound. So potassium selenide. So potassium from the periodic table is just potassium plus selenide, IDE. This is derived from selenium, which is at Se2-. We know this because potassium is a 1A element, so it prefers a +1 charge. Selenium is a 6A element, so it prefers a 2- charge. After we cross both of our charges into the subscript, we get potassium selenide. Any questions on this example? Any questions on this example?
So what, sorry.
Oh, no problem at all.
So why does the 2- end up being positive, but the plus doesn't end up being negative?
Because a subscript, if it's representing the number of atoms, you can't have a negative subscript by definition because there's no such thing as a negative number of atoms. Does that make sense?
So the second portion will always be positive? Like,
You mean the subscripts will always be positive. The charges can be positive or negative, but the subscripts, which are the numbers indicating the number of each cation or anion, those will always be positive because they're representing the number of each cation and anion.
okay, so let's say the K had a -3 or -3, that would still,
Yes.
so that would be up there, right?
Yes, but I do want to say that usually the cation is written first, followed by the anion.
Okay.
Yeah.
Thank you.
Mhm. So let's work on a few more examples. So I'll do the first two. And let's write the formula for the following compounds. So for lithium sulfide, lithium we get from just the name of our metal. Sulfide is derived from sulfur. Lithium is a 1A element and sulfur is a 6A element. So we would expect lithium to adopt a +1 charge and sulfur a 2- charge. We then cross our charges and that in turn gives us lithium sulfide. Let's do this next example, cesium oxide. So we have cesium and oxide, we have oxygen. Cesium is a 1A element. Oxygen is a 6A element. Again, cesium has a +1 charge. Oxygen has a 2- charge. We cross our charges and that in turn gives us cesium oxide. Any questions on this example? Any questions on this example? If not, let's take about 3 minutes and let's try to write out a valid formula for the following compound names. So this is really important because you may start to see problems in later chapters that provide you the name of each compound rather than just giving you the formula directly. Let's try to get a few responses in the chat and a few questions in the chat, and we'll discuss in about 2 to 3 minutes. Let's try to get a few more responses in the chat, and then we'll discuss momentarily. So let's discuss this next example. So aluminum oxide. So aluminum from the name is just the symbol Al. Oxide indicates we have oxygen. Aluminum is a 3A element. Oxygen is a 6A element. Aluminum adopts a charge of +3. Oxygen adopts a charge of 2-. We cross our charges, and that gives us Al2O3. Let's look at barium chloride now. Barium represents the symbol Ba. Chloride represents the symbol Cl. Barium is a 2A. Chloride is a 7A element. Barium adopts a +2 charge. Chloride adopts a -1 charge. We cross our charges, and that in turn gives us BaCl2 for barium chloride. Any questions on these examples? Any questions on these examples? If not, let's continue on. So what we're going to do is, so that way we have enough time for the laboratory exercises today. What we're going to do is we're going to take and pause our supplemental lecture. We'll continue this lecture on Monday. We're now going to switch gears and focus on the laboratory experiments. We'll perform the neutralization experiment, and once we finish the neutralization experiment, we'll talk a little bit about nomenclature.